The light that seems so simple. You walk into a room in the evening and reach for the light switch almost without thinking. Your fingers find the familiar little rectangle on the wall. You press it. Click. A moment later, the room is bright enough to see everything around you. You have performed that tiny movement thousands of times. Perhaps you do it while carrying a cup of tea, while looking for your glasses, or while walking through the house before everyone else is awake. It feels almost too ordinary to notice. But underneath that ordinary click, something remarkable is happening. The light does not seem to wait. You do not watch anything crawl visibly through the wire. There is no obvious journey from the power station, through the walls, and finally into the bulb. You simply move your finger, and the bulb responds. Naturally, your mind fills in the missing story. Somewhere, you imagine, electricity travels through the wire toward the light. Perhaps you picture tiny particles rushing along the metal, carrying energy with them like water moving through a pipe. That picture is familiar. It is also incomplete. And this matters because electricity is not some rare phenomenon you encounter only in a laboratory. It surrounds your daily life. It powers the light above your head, the refrigerator in your kitchen, the phone charging beside you, and countless devices you rarely stop to think about. You already know what electricity looks like when it works. What you may never have been shown is what is actually happening underneath that simple click. And the difference between what seems to happen and what actually happens changes everything you were taught. Once you look closely, the ordinary light switch becomes something much more interesting, a small doorway into one of the most misunderstood ideas in modern physics. The picture in your head. And that missing piece begins with the picture in your head. Most people were taught to imagine electricity as a stream of tiny particles leaving a battery or power station, traveling through a wire, entering a device, and delivering energy. It is an understandable picture. For basic purposes, it can be useful. But when you treat it as a literal description, problems appear quickly. For one thing, electrons are not simply being used up by your lamp. They do not disappear when the light comes on. The metal wire was already filled with mobile electrons before you touched the switch, and the wire itself is not an empty pipe waiting for electricity to arrive. That distinction is easy to miss because everyday language encourages it. You say that electricity comes into your house. You say that a battery supplies electricity. You say that a device uses electricity. Those phrases are convenient. None gives you the complete physical picture. Here is where the mystery becomes difficult to ignore. When you switch on a light, the response is immediate enough that you never sit there waiting for electrons to make their journey from a distant power source. The electrons in the wire do not need to race through your walls at anything resembling the speed of light. Yet the lamp responds. You already have everything needed to explore this sitting around you. A flashlight, a charger, a lamp, or even the wires hidden behind that wall switch. So if the electrons were already there, and they are not racing from the power station to your light, what changed when your finger pressed that switch? Before we replace that familiar picture with a better one, there is a reason the simpler explanation became so deeply embedded in the way we talk about electricity. The problem with simple explanations. And that is where simple explanations become a problem. Not because they are always wrong, but because a useful analogy can quietly become the thing you believe is actually happening. You have probably seen electricity explained as water moving through pipes. Voltage becomes water pressure. Current becomes the amount of water flowing. Resistance becomes a narrow section of pipe. For an introductory lesson, that comparison can help you understand relationships between electrical quantities. But there is a line between using an analogy and mistaking the analogy for reality. A metal wire is not a water pipe. Electrons are not little droplets of water. And electrical energy does not simply behave like a substance being pushed down a hollow tube from one place to another. This is where I find many explanations frustrating. They give you a picture that feels intuitive, then stop just before the picture starts raising difficult questions. What actually changes when you close a switch? Where is the energy before the lamp lights? How does the circuit respond so quickly? And what role does the space around the wire play? Those questions lead somewhere much more interesting than the usual classroom metaphor. This is also where the style of Richard Feynman's thinking becomes useful. Feynman repeatedly encouraged people to strip away the labels and ask what nature is actually doing. Instead of memorizing that voltage is pressure or current is flow, you can ask what is physically present, what forces act on charges, and how energy moves through the system. The deeper answer involves electromagnetic fields, which are not mystical, invisible fluids, but physical fields that describe how electric and magnetic forces are distributed through space. That distinction changes the entire picture. The popular version says electricity is like water flowing through a pipe. The deeper physics says current describes the motion of charge, while electromagnetic fields provide the framework through which energy is transferred to the device. And once you see electricity this way, several ordinary electrical mysteries stop being mysterious at all. You can stop memorizing the metaphor and start understanding the mechanism beneath it. This is what understanding means. That is the kind of understanding this channel is built around. Not memorizing impressive words, collecting scientific trivia, or pretending that a complicated subject becomes simple because someone gave it a clever analogy. The goal is more useful than that. You should be able to look at something ordinary, like a lamp turning on, and understand enough of the underlying physics that the event begins to make intuitive sense. You do not need to become a physicist. You simply need a mental model that holds together when you look at it closely. If this kind of explanation is useful to you, consider staying with the channel. There is a great deal of fascinating science hidden inside things you encounter every day, and we will keep approaching those subjects by asking what is actually happening. For now, return to that switch. The instant it closes, the real story begins, and this time we will follow it one physical step at a time. What electricity actually does. The first thing to understand is surprisingly simple. The wire is not empty. Before you turn on the lamp, the metal inside that circuit already contains an enormous population of mobile electrons. A battery does not manufacture a fresh stream of electrons and send them racing toward the bulb. The charge carriers are already there, throughout the conductor. That immediately creates an important distinction. An electron can move through a wire while the electrical effect that influences it propagates through the circuit much more quickly. The average net motion of electrons, called drift velocity, can be quite slow. In an ordinary conductor, individual electrons do not need to sprint from the power source to your lamp for the lamp to respond. This is one of those details that sounds almost backwards until you separate motion from influence. Imagine a long line of people already standing shoulder to shoulder. If the person at one end moves, the effect can be communicated through the line without that same person traveling all the way to the other end. The analogy is imperfect, but it gives you the basic intuition. The particles themselves and the propagation of an electrical change are not the same thing. Now consider voltage. You have probably heard that a household outlet provides around 120 volts in some countries, while many others use around 230 volts. But voltage is not a quantity of electricity sitting inside the outlet. It is a difference in electric potential. The word potential can sound abstract, so think briefly about height. A book sitting on a high shelf has gravitational potential energy because of its position relative to a lower place. Voltage is not the electrical equivalent of height, but the comparison helps. A difference in electric potential establishes conditions under which charges can move and energy can be transferred. Voltage is not current. Voltage is not a fluid. And voltage is not a mysterious substance flowing down the wire. Current describes the rate at which electric charge moves through a circuit. Voltage describes a difference in electric potential that can drive that charge movement. Then you close the switch. This is the turning point. The switch does not sit there waiting for a packet of electricity to arrive from the power station. Closing the circuit changes the electromagnetic conditions of the system. An electric field is established through the circuit, and that field exerts forces on the mobile charges already present in the conductor. The response of the circuit is therefore not a simple story of one electron beginning a long journey. Something changes throughout the electrical system. That is why a lamp can respond so quickly. The individual electrons have not suddenly become extraordinarily fast. Instead, the electromagnetic disturbance that establishes the relevant electric field propagates through the circuit at a much higher speed, determined by the physical structure and surrounding materials of the circuit. In practical electrical systems, this propagation can be a substantial fraction of the speed of light, although it is not automatically equal to the speed of light. And now we reach the distinction that makes the entire subject clearer. Charge movement and energy transfer are not identical. The electrons are the charge carriers. They respond to the electric field and participate in the current. But the energy delivered to a component is described by the electromagnetic field surrounding the circuit. Physicists formalize this using something called the Poynting vector. The name sounds intimidating, but the underlying idea is remarkably useful. It gives us a way to describe the direction and density of electromagnetic energy flow through space. You do not need the mathematics to appreciate the implication. Energy associated with an electrical circuit can be transferred through the electromagnetic field into a device. It is not necessary to imagine energy as a substance being carried inside the electrons, like tiny parcels in a delivery truck. This is precisely where the water pipe analogy starts to crack. Water really does move through a pipe as a material substance. An electrical circuit is more subtle. Charge moves through the conductor, while electromagnetic fields participate in transferring energy to the component that uses it. Now look again at your lamp. An appliance does not simply receive electricity and then somehow become bright. Something physical happens inside it. In an incandescent bulb, the current encounters resistance in a thin filament. Electrical energy is converted into thermal energy, making the filament extremely hot, and some of that energy leaves as visible light. An LED works differently. It uses semiconductor materials in which electrons and other charge carriers interact with electronic energy states, producing photons when energy is released. Different device, different microscopic process. But the larger chain remains. The electrical system establishes conditions for current. The current interacts with the device. The device converts electrical energy into another form: light, heat, motion, sound, or stored energy. And notice how ordinary the numbers are. Household alternating current typically changes direction 50 or 60 times per second, depending on the electrical system. A 120 volt or 230 volt supply tells you about the electrical potential difference, while power is described by the relationship P equals V times I. If a device draws 2 amperes at 120 volts under suitable conditions, its electrical power is 240 watts. Over time, the energy delivered is related to power multiplied by time. These relationships are not tricks for passing a physics exam. They describe what your appliances are doing every day. And there is one final piece: the battery. A battery is not a tank filled with electricity waiting to spill into a wire. It stores chemical potential energy. Chemical reactions inside the battery create an electromotive force, which establishes an electrical potential difference across its terminals. Once the circuit is completed, that potential difference helps establish the electromagnetic conditions that drive charge movement and enable energy transfer. So the chain becomes much clearer. Chemical energy establishes an electrical potential difference. That potential difference establishes electromagnetic conditions. The electric field influences charges already present in the conductor. Current flows. The electromagnetic system transfers energy to the device, and the device converts that energy into something you can see, feel, hear, or use. That is why the light turns on. Not because a mysterious substance finally arrived at the bulb. Once you see that distinction, the switch becomes less like a gate releasing electricity and more like a control that changes the electromagnetic conditions of a circuit. And this is exactly where the familiar explanation begins to fail. Because most people picture electrons doing something very different from what the circuit actually requires. The electron traffic jam that isn't there. And that distinction gives you a much better way to understand the common picture of electricity. You may have imagined electrons as tiny bullets leaving the battery, racing through the wire, reaching the appliance, and delivering their energy. It is an intuitive picture. It also creates a problem. If the electrons themselves move relatively slowly, why does the lamp respond almost immediately when you close the switch? The answer is that the electrons do not need to make that journey. The conductor already contains mobile charge carriers. When the circuit is completed, the electric field changes the conditions throughout the circuit, influencing charges that are already present. Their local motion contributes to current, while the electromagnetic field participates in transferring energy to the device. That is a very different story. The version most people have heard is that electrons leave the source, travel through the wire, arrive at the appliance, and deliver electricity. But what the physics actually describes is more subtle. Charge carriers are already distributed through the conductor, electromagnetic fields establish forces on them, and energy is transferred through the electromagnetic system into the component. And you were not wrong to picture it the simpler way. That model was useful for introducing electricity. The problem came when the teaching stopped there. This is why replacing the mental picture matters. Once you understand that the wire is already populated with charges and that electromagnetic fields help establish energy transfer, the old image starts to feel less convincing. But there is an even deeper misconception hiding underneath this one, and it concerns what you think electricity itself actually is. Electricity isn't a substance. Once you stop imagining electrons as tiny bullets, another assumption becomes easier to see. You have heard people say that electricity flows through a wire for years. It sounds natural. Water flows through a pipe. Air flows through a vent. So electricity must be an invisible substance moving from one place to another. That idea did not appear from nowhere. Everyday language needs simple words for complicated events, and electricity became a convenient umbrella for related phenomena. The language is useful. Trouble begins when the metaphor becomes physics. Electric charge is one thing. Electric current is the motion of charge. Voltage is a difference in electric potential. Electrical energy is the capacity to do work. An electric field describes how electric forces are distributed through space. These are connected, but they are not interchangeable. The version you have been given may compress all of them into one sentence. Electricity flows through the wire. The deeper physics says something more precise. There is charge in the conductor. An electric field can exert forces on that charge. Current describes the resulting charge movement, while electromagnetic fields provide the framework for understanding how energy is transferred through the circuit. This distinction appears throughout serious electromagnetic physics. Richard Feynman's lectures on physics repeatedly emphasizes the importance of building a physical picture rather than relying on words alone. James Clerk Maxwell's electromagnetic theory gives us the broader framework in which electric and magnetic fields are related, while Poynting's theorem provides a formal description of electromagnetic energy flow. You do not need to memorize those names to understand the point. Electricity is not a mysterious fluid that can be poured into a battery, stored like water, and later emptied through a wire. The word describes electromagnetic phenomena, and that gives you permission to keep using the word without being trapped by the metaphor. When you say electricity is flowing, you can understand that this everyday phrase is shorthand. In a more precise description, charges are moving, fields are changing, potentials establish electrical conditions, and energy is being transferred and converted. That is a richer picture than the one you were probably given. And once you separate those ideas, an ordinary electrical device begins to look different. The switch is no longer simply releasing electricity into a wire. It is changing the conditions of an entire electromagnetic system. That is the piece we can now make practical. The 60-second electricity experiment. Now you can test this mental model without opening a wall outlet, touching exposed wiring, or building anything complicated. Take an ordinary battery-powered flashlight. Hold it in your hand and look at the battery for a moment. Instead of picturing a tank filled with electricity, picture chemical energy stored inside the battery, capable of establishing an electrical potential difference across its terminals. Turn the flashlight off. The circuit is now interrupted, so there is no sustained path for current through the lamp. Then switch it on. The moment the circuit is completed, the electrical conditions change throughout the circuit. The electric field influences charges already present in the conductors, current flows, and the device begins converting electrical energy into another form. In a flashlight, that becomes light, along with some heat. Now ask yourself a different question. Do not ask, which electron traveled from the battery to the light? Ask, what changed throughout the circuit when the connection was completed? That second question is much closer to the physics. You can even repeat the experiment several times. Off, on, off, on. Each time, you are watching the same chain unfold. Chemical energy establishes a potential difference. The electrical system establishes fields. Charges respond. Current flows. And the device converts energy into something useful. There is something important about doing this with a simple flashlight. You are not being asked to memorize a new definition. You are training your mind to see an ordinary event differently, and that skill transfers everywhere. The same basic questions can be applied to a lamp, a motor, a phone charger, or another electrical device. Where are the charges? What fields are present? And where is the energy being transferred? For safety, keep this experiment strictly to intact, commercially manufactured battery-powered devices. Never open mains electrical equipment, touch exposed household wiring, or experiment with wall outlets. If a device is damaged, leave it alone. The remarkable part is that you can perform this observation in less than a minute, yet the idea behind it reaches from a small battery to the electrical systems powering entire cities. That is why this simple observation matters. It turns an ordinary object into a doorway for understanding. You have just turned a familiar flashlight into a small physics lesson, and suddenly, the switch you have flipped thousands of times is no longer an ordinary piece of plastic. It is the point where an entire electromagnetic system changes dot. The switch in your hand. Think back to that moment we started with. You walk into the room, reach for the switch, and hear that familiar click. But now, you see something different. You are not imagining electricity racing through an empty wire like water through a pipe. You understand that charges are already present, fields establish the electrical conditions, and energy is transferred and converted by the device. That tiny click represents something much deeper. Every single time you turn on a light, the same fundamental principles are unfolding. Once, twice, hundreds of times a day, every day. The ordinary has become understandable, and that changes how you see it. Learn to see ordinary things differently. If this kind of explanation is useful to you, consider staying. This channel is built around taking familiar things you have seen your entire life and revealing the deeper science underneath them, one clear idea at a time.